Hi there and welcome from Ventura, California to today's webinar, Autonomous Week Day 2 Machine Control, sponsored by Inside GNSS, Inside Unmanned Systems, Hexagon Novotel, Spirent Communications, and SBG Systems, and hosted by WebAttract. I'm Lori Dearman, Senior Webinar Producer with WebAttract, and I'll be one of your moderators for today's session. And in just a moment, we'll be introducing our panel of thought leaders as today's webinar features expert insights and key technology aspects of sensors, platforms, and integration for implementing autonomy. Today is day 2 of our 3-day series, which focuses on machine control in construction and mining. Now, we've invited you, along with over 450 professionals, registered from 52 countries, representing a variety of industries. And over the next 90 minutes, regardless of your segment of industry or your location, we're confident that you'll find today's webinar of value. Now, before we get started, Richard Fisher, publisher inside GNSS and Inside Unmanned Systems, would like to take just a moment to welcome you and introduce our main moderator for today's session. So over to you, Richard.
Thank you, Lori. Welcome all for day 2 of Autonomous Week. So on behalf of Inside GNSS, Inside Unmanned Systems, and all of our sponsors, we very much appreciate your attention and participation, and we welcome you to day 2 of Autonomous Week. It was 6 years ago when we launched Unmanned Week. Much has changed. I'm particularly interested in today's subject matter on machine control. We have a stellar lineup for you today, and we're going to learn about many of these developments over the past 6 years. So we're really looking forward to this talk today. So I'd like to introduce today's moderator, Editor-in-Chief of Inside GNSS and PNT Editor of Inside Unmanned Systems, Alan Cameron. Alan, please.
Thank you, Richard. Hello, everyone around the world. It's good to see once again an international audience gathered for this high-level, deep-dive technical session. Today, focusing on machine control. We're in the middle of Autonomous Week. Even though it's Thursday, we're packing a week's worth of technical training and education into 3 days. And as we've said, today's focus is machine control. Thanks to our sponsors, Hexagon Novotel, Spirent Communications, and SBG Systems. We'll be hearing from each of these companies, leading experts on their staff, talking about their particular areas of professional focus and how they will benefit you. You can see them there, Lee Baldwin from Hexagon and AutonomouStuff, Rafael Gretsch from Spirent Communications, joined by his colleague Ali Soliman, and Alexis Guinamard from SBG Systems. Before we hear from our first panelist, who will be Lee Baldwin, Lori, let's find out a little bit more about our audience.
Yes, let's do that. Coming up on the screen is the first of our poll questions for today, and we're interested in hearing from each of you. What level of positioning accuracy does your application require? If you'd go ahead and select one of those options, 0 to 10 centimeters, 10 to 50 centimeters, 50 centimeters to 1 meter, or perhaps greater than 1 meter. Okay, looks like 55% saying 0 to 10 centimeters, 18% saying 10 to 50 centimeters, 25% of us saying 50 centimeters to 1 meter, and 2% saying greater than 1 meter. So, Alan, any thoughts here?
Well, we, with that commanding majority at 0 to 10 centimeters, we are in the machine control zone. That's not to say that the others with lesser requirements are not going to find plenty of valued information in this webinar. There are certain aspects of machine control also that involve the lesser accuracies, which is not to say that 1 meter of accuracy is anything to sneeze at. Let's go ahead and hear from our first panelist. Lee Baldwin is the Director of Off-Road Autonomy at AutonomouStuff. He's responsible for creating and implementing the off-road autonomy product strategy that aligns with the AutonomouStuff mission and values. He spent the last 10 years as an engineering manager at Caterpillar, where he led development of the command and control portion of the autonomous hauling system. Lee, we're all anxious to hear your presentation. Please go ahead.
Thank you, Alan. Appreciate the introduction. So today I would like to spend about 15 minutes. I'll talk a little bit about autonomous stuff and a role with Hexagon. Then I would like to spend some time on onboard autonomy components in the subsystems that you'd find typically on any autonomous machine. Then I'll spend a bit time into the perception subsystem, which is one, obviously, of the critical systems that you need in a robot, and talk about a real-world use case. And this use case is going to flow through each of the speakers, autonomous hauling and mining, and lots of nuances. And that was the first application, really, from an autonomy standpoint to kind of mainstream. And then I'll finally talk about kind of the road to production and how you would do that in the context of training perception systems. So first, autonomous stuff, briefly, it's been around for about 10 years. Small startup company, started out of Morton, Illinois, and grew into a kind of globally recognized brand, especially when the looks of from an R&D standpoint and autonomy. And then what autonomous stuff really people notice this for is being able to get access to components, autonomy components, where some of the suppliers and manufacturers only want to deal with major volume, and that's where we've come in to help universities, tier 1s and OEMs. And then the other thing that we've done is pretty good is the drive-by-wire systems for machines. We'll basically go into a machine and make it so a computer can control that machine. And we've taken a variety of on-road and off-road vehicles and done that. And in the last couple of years, we were acquired by Hexagon. So Hexagon noticed the value that we were bringing, and we worked a lot with them on the GNSS receivers, Novatel. So Hexagon, at least the division that we're in, autonomy and positioning, is got a nice global footprint. So a lot of manufacturing done in Calgary and various marketing offices throughout the world. So what I like to do is talk about the subsystems for autonomous driving. And these will be the same subsystems that you would find in off-road or on-road vehicles. You'll hear a lot about the positioning subsystem, obviously, this week. So I'm not going to talk too much about that. It's obviously super important. That you have a planning subsystem. You have this drive-by-wire system that actually controls the machine. And then you have perception. And perception is really what the robot or machine sees in the world. So it's the sensors and the components that make up how it perceives reality. So the important thing to take away is there's a few subsystems that make up the machine. And then what you'll typically find is off-road machines will have a command and control aspect of it. And that's what I spent about 10 years on, working for the command and control aspects of an autonomous hauling system, and which is, again, I think one of the first applications where were fully autonomous machines running around in a production sense. So perception, we want to talk a little bit more about perception. So in the vehicle platform, so this is typically, you'll find some of these sensors on any machine, autonomous machine. And depending on the use case and where that's being used, they'll have a stronger reliance on certain machines, on certain components. Obviously, you'll find GNSS receivers and IMUs because the position is obviously very important for the autonomous machine. But then the perception system, you'll see a variety of sensors and potentially fused together. You could see cameras for object detection and object categorization. But you can also do that with radar and LiDAR. So depending on the environment, you may use one or all of those sensors. And then you'll see a drive-by-wire system. Again, the interfaces with the machine systems and provides and gets feedback from them. So any machine, you'll see these things. And some of the interesting things are with camera technology, thermal cameras for night vision and things like that. So just some of the common components that you'll see. And some of the applications, we're talking about off-road autonomy today and where this is going. So obviously mining has been on the forefront of that. Agriculture is there's many startups out in agriculture working on robots because of the scarcity of labor. Shipping ports, you already see the gantry cranes, but there's a push to automate other aspects of ports. Airports, due to the damage to airplanes and things like that, you can see automating certain vehicles at an airport around them. Obviously, a lot of military applications and facility logistics or little shuttles. So one thing you'll see in common about many of these, except for airports, is they can be enclosed environments. So what this is from an off-road environment. This is one of our research and development vehicles that it's a Polaris Ranger. And this showcases perception systems. So in this case, this is the LiDAR point cloud that's coming out. This is a thermal camera used in perception as well. In this is the show that our drive-by-wire system is actually controlling the Ranger with no safety driver. And you'll see coming up that it stops. That's one of our engineering managers, and it will stop and void and automatically restart and carries on. So that's just some of the things that we've done with off-road vehicles, but we've done quite a few passenger vehicles as well. Okay. So now I'd like to go into perception systems, spend a little bit of time on that. And typically you'll see perception systems, they're using some sort of neural network or artificial intelligence. You'll see, typically a camera fused with something else, and that could be a radar or a LiDAR. The camera could be used for both object detection and classification, and then utilizing a fusion of a radar, a LiDAR to get the distance to the object. And you could also see toward the right that this is a thermal camera operating, and we find thermal cameras quite interesting because they operate both in day and night as well. And what you're seeing here is this is something our neural network experts have been working on, is just some object detection classification with just cameras on the left, and then fusing camera and radar. So what you notice on the left, you'll see, you might not be able to read what's in the caption, but it's basically saying what it's found and the percentage confidence that it thinks it's that. So obviously the more you train a neural network with more data, you teach it, and it'll get more accurate. And then toward the right, this is where we fuse the sensors so that one of them is figuring out the distance to the object and comparing it to the other one. Obviously radar is really good at that, but you can get pretty good results out of cameras too. And here's a demonstration of similar object detection classification in off-road environments. You got mining and ag. And on the right, this is a real-time semantic segmentation view of a mine. And you'll see the haul road in green and the berms that are not drivable in the orange. And so you would do this to detect the drivable area in a mine. And even if it's not an autonomous vehicle, it could be for a driver-assisted system. And then how do you go about doing this? Well, training these neural networks or these artificial intelligence, which you basically need lots of data, tens of thousands of images to train a neural network to detect an object and classify it properly. Now, some of the challenging parts of it is one, just getting the data. And sometimes you have use cases that are dangerous or something else. So what we found is utilizing simulation and specifically utilizing game engines, Unity and the Unreal Engine to generate scenes and that are fully annotated already, meaning annotated bounding boxes, or it could be full semantic segmentation, and extracting the gaming data and teaching the neural network through that, and basically iterating it with both synthetic and real images gathered to get better results. So I think that's interesting. Is the part is the use cases and the edge cases that you just can't get in the real world because it'd be dangerous. So what I want to talk about briefly is autonomous hauling for open pit mining. So I have some experience with this. Western Australia was really the South America, where there was some test mines in there, but Western Australia, where it really went out, was big. And why autonomous hauling? And it's really been around for about a decade. And it's mainly due to scarcity of labor, just the cost of labor for haul trucks. You need basically 4 drivers for every machine. And then the other thing is safety. Robots don't fall asleep. You just fuel them once or twice a day, and you're good to go. There's no brakes. So, but the primary reason was labor and just the cost. And but what I found is that the productivity is actually higher than a man truck for some of those reasons. So how did autonomous hauling evolve? Well, it evolved from manual fleet management. We have always had these large enterprise applications that orchestrate an open cut mine to make it more productive. And those evolved into robots and adding and extending them to handle robots. And the good thing is the robots always just do what they're told, and then you can also do things with them, derate an entire fleet if it's raining. When rain hits iron or the clay, it gets very slippery. So there's a lot of things you can do. Difference in on-road driving and autonomous hauling. Big differences are just the number of corner cases, edge cases, and the fact that in autonomous hauling, you can have a command and control piece of software that works with that fleet management that controls the closed area where the robots operate. You obviously don't get that in real-world driving, and everything truly is autonomous. Where these trucks, they're autonomous, but they also have something else that they can rely on to help keep things safe. And you can control things like people. You just keep them out of the area. And that's where port autonomy, you can control what goes in and out of the area and agriculture. And the same thing, I know there's a number of defense folks on. Same thing obviously applies to missile ranges and things like that. Autonomous target practice and things like that is a big deal for these. And you can control it. My final slide is really the workflow and how you go about doing the training. And this is largely related to the perception subsystem. But really what you need is a lot of data, and you have to acquire the data. So you'll typically have this data acquisition phase where you're just gathering data with your targeted sensors. And then you have to classify it and label it. I mentioned annotation, but basically you have an outside third party draw boxes around the objects that you want to classify. And then you train it in the application development, and you just keep doing this over and over again. And specifically in simulation, probably 90% would be done in simulation when only 10% on the real world. And then finally you come out in the real world and do that. So this is in a nutshell, very quick kind of primer on autonomous hauling and some of the key aspects of a perception system and how to go about it. So back to you, Alan.
Thanks very much, Lee. We've had a couple of questions come in about your presentation. We'll turn to those in another few minutes. We're going to hear from Raphael next, and then halfway through his presentation, we'll pause to field a couple of those questions. Raphael Gretsch, PhD, is the Business Development Manager for Connected and Autonomous Vehicles at Spirent Communications, where he's responsible for engaging the market and further potential collaborators within the connected autonomous vehicle industry. He provides early engagement to help Spirent refine and further define potential product offerings and provide periodic updates to the business plan. He's also responsible for establishing links between the sales channels and the business unit in the UK for new PNT connected autonomous vehicle applications, enabling new customer arrangements and new engagements and new business, and influencing the business unit to be timely and responsive to meet new business needs and provide technical and solution expertise. This goes together with development activity, looking for further exploitation avenues to take work from technology demonstrators through to full product solutions. And as we just heard from Lee, a simulation is key to that step. Raphael, please give us your presentation.
Thank you, Alan, for the introduction, and hello, everyone. So, yeah, as Alan mentioned, this is a double act from Spirent. So in the first half, I will look at the more recent challenges, the development for GNSS positioning technology within autonomous systems. And in the second half, my colleague Ali will show you how this all fits within an application use case, which in this case is in one of an open pit mine. So, the first question that comes is like, how much do you trust your sat-nav? So currently, the human driver takes responsibility of driving and uses the GPS navigation only as guidance to inform them of their current location. As we can see from these images, there are situations where the sat-nav would provide inaccurate information, and the driver is expected to ignore the sat-nav suggestions and localize and navigate accordingly. Again, as we can see from these pictures, some of the drivers would ignore these warnings and trust the sat-nav blindly to an extent that they would end up in very awkward situations. So this poses a very interesting challenge. So what we say here is that it is good to be aware of the receiver and sat-nav limitations, and yes, you should trust the position, but at the same time, you need to make sure that you verify that what you're getting is true. So what we're seeing here in this slide is that improving the position accuracy of mobile devices has been the goal of several industry segments for decades. Some of the industry include robotics, shipping, fleet management, and more recently, also autonomous vehicles and unmanned aerial systems. Precision agriculture and mining are also two segments which are becoming more heavily dependent on position accuracy. Looking at the top image, we can see that the more traditional GNSS and IMU combination is fairly mature and well-adopted technology. We also see that several other techniques are coming into play, such as the use of RTK and PPP. We are also seeing the introduction of other sensors, such as cameras, LiDAR, and also more complex mechanisms coming from the mobile robotics domain, such as visual navigation and SLAM, which stands for simultaneous localization and mapping. This is the combination of building a map of your environment, whilst at the same time, you're trying to localize yourself within that map to reflect where you are in the real world. In this chart, we're seeing that the automation levels for different segments ranging from aviation, automotive, and maritime. What is common between these segments is the fact that as the automation level increases, so does the system complexity. If we focus on positioning and localization, it becomes clear that, as explained earlier, augmentation systems are required to achieve the integrity levels required for such autonomous systems. On this chart, excuse me, on this chart, we are seeing the main errors which the environment introduces on the GNSS signal from the satellite all the way down to the receiver. Also, the table on the right-hand side shows the error budget and the expected error introduced by each segment. The good news is that there are already several market-available augmentation services such as RTK and PPP, or the combination of both. These augmentation and correction services compensate the satellite orbit errors and ionospheric and tropospheric delays. The downside of such systems is that they generally assume an open sky and they do not reflect the obscuration, multipart, and the receiver bias still need to be accounted for. These would happen more often in dense urban environments, forests, and cliff faces. Also, this will be discussed in more detail further on in the presentation, and Ali in the second half can show you even more about this. So, as the levels of automation in vehicles increases, so does the complexity of the positioning engine. More traditionally, the positioning engine uses solely the GNSS receiver. This was eventually further enhanced using motion sensors such as inertial measurement devices and odometry. And there are also some very good implementations available already in the market. This, however, might not be good enough for certain applications, especially where the environmental awareness is required for positioning engine to assist in localization and map building. To do so, other sensors such as camera, LiDAR, and radar also feed into the positioning fusion mechanism. This is generally not only required to have a level of redundancy, but is also needed to improve the vehicle estimated position with a higher level of accuracy and the integrity required for high automation levels. So this is quite an interesting shift in the way that we look at positioning and localization. So the main shift is that rather than just us focusing on getting a position and then we have humans to decide if that position is accurate or not, now all of this has to happen through the positioning engine mechanism and the control system which is controlling the vehicle. So as mentioned in the first couple of slides, where people make mistakes even though they are warned through signs, imagine if this system which has to rely on the positioning available from the positioning engine is not accurate. So that's basically the takeaway message that I would like to leave you with, as in we need to make sure that whatever we're receiving is accurate and as precise as it can be. So that's all from me for today. And in the second half, my colleague Ali will show you how all of this fits within an off-road open pit mine application. So thank you again, and back to you, Alan.
Thank you, Raphael. We're going to pause briefly for a few questions from the audience, and as Raphael said, his colleague Ali will then take up the stream after this short break. A couple of questions have come in for you, Lee. The first one, how does one ensure accurate positioning of an off-road autonomous machine?
Yeah, that's an interesting one, especially in remote areas where you're away from mobile networks and things like that. So the first thing is you want to do as much as you can on the machine. So that would be, redundant GNSS receivers that see multiple constellations. Obviously, RTK and corrections. So the corrections is an interesting thing. You probably need a local base station. And you also want to make sure is you test the local base station to ensure that it's hasn't been moved. Because as you can imagine, if somebody moves your base station, off a bit and you're in a mine with a bunch of haul trucks running around, you could shift where the system thinks all the trucks are. So the base station is key. You need some sort of method to make sure your base station is solid. And then I guess an IMU. And the combination of all those things, you can be pretty certain that you know where each machine is exactly on that mine site.
Thank you. Now, we haven't heard from a couple of our other panelists yet, but I want to encourage everyone to jump in if you have anything to add to anyone else's answer as we go along. Another question for you, Lee. AutonomouStuff has experience with full stack autonomy systems. Which systems that you are familiar with, and or please go over the systems that you're familiar with and the pluses and minuses of each.
Mm-hmm. Well, the context shifts a bit to on-road driving for that. So the two full stack autonomy systems for essentially on-road driving that we actually integrate and install on machines are Apollo, which is from Baidu, and AutoWare from the AutoWare Foundation. And basically, if you either one of those gives you some form of an SAE level 3-4 self-driving car on a roadway. So Apollo's probably been around a little bit longer, so it's a bit more feature rich, but from an open source standpoint and able to go in and change things, that's where AutoWare, I think, probably beats it. If you're trying to learn more about perception systems or path planning or something like that, the open source is a good way to do it. Especially we've seen that in academia. If somebody wants to get an autonomous vehicle, passenger vehicle running, those are probably the easiest ways to do it with those. That's it.
Yeah, for the benefit of the audience, I've myself had a bit of an opportunity recently to get familiar with AutoWare, and that's exactly right. The open source aspect of it allows the developers to see the inner workings and perhaps manipulate the inner workings. Just because it's open source doesn't mean that you can read it like an open book. Some guidance from AutonomouStuff is going to be necessary there to get you familiar with the various stacks and how they interact. But it's a great tool for developing new applications or adapting functions that you may know, adapting them into an autonomous framework. Raphael, we had one question for you. How can simulation and real-life testing be balanced in order to get the maximum benefit of each methodology?
Yeah. So that's a very interesting question. So the challenge in finding a balance between simulation and real-life testing is the fact that depends on the stage of the development. So it is true that if you have a prototype which you want to test, you can go out and see how it performs. But then again, it's very hard to repeat. And that therefore provides the need to kind of have a repeatable test, especially during the development. Now, there are situations where simulation can, as in the only way to do it is through simulation, because you want to have a proper repeatable test, and you need also, you might be testing for some specific satellites or a specific constellation. However, there's only so much with a simulator can give you. So the main focus, I would say, is ideally you need to make sure that when you're testing in real life, especially if you're capturing data, that tends to be more expensive than the simulation. So it's it's finding the right balance with finding what are the edge cases, using a simulator potentially to identify when these will actually happen in the real world, and then go out in the field. You have enough time to plan for it. You know exactly what you're going to capture. And potentially, rather than just using the simulation for development, you might also want to use the simulation to identify when the challenging scenarios are actually going to happen in real life, and use that as well, so that you can have not only efficiency in finding when the data that you really need is actually going to happen, but you also save in terms of cost and engineering effort, in the sense you know what you're going to expect when you go out in the world. Again, Ali can give you even more information about this further on, and we will discuss it in even more detail tomorrow.
Right. We'll continue with Ali in just a moment. And as Raphael pointed out, there's more to come tomorrow, and some really significant developments to be unveiled tomorrow in new platforms. Before we continue with our presentations, Lori, let's learn one more thing about our audience, if we can, please.
All right, yes, let's do that. On your screen is that second poll question, and we're asking, what types of PNT errors are you most concerned about? Again, selecting one of the following four choices: GNSS obscuration or lack of availability, GNSS interference, jamming, or multipath, inertial system drift, or errors from other PNT sensors. Okay, it looks like 31% saying GNSS obscuration or lack of availability, 51% GNSS interference, jamming, or multipath, 15% inertial system drift, and 3% errors from other PNT sensors. Thoughts here, Alan?
Well, as we see in almost everywhere we look, or as I see in almost everywhere I look, whether it's at technical conferences or in conversations, private conversations with designers and engineers, interference, jamming, or multipath lead the concerns when we're talking about GNSS, followed by obscuration or lack of availability, just getting a good usable signal. Now, as you combine it with inertial, you have to govern your error budget in that respect as well, but it appears to be of less concern, at least at the moment. We're going to continue with more material about simulation, and then we will turn to that last subject, inertial technology, in today's webinar. For more simulation information, we'll hear from Ali Soliman, Business Development Manager for GNSS PNT Technologies and Connected and Autonomous Vehicle Testing Systems at Spirent Communications. Ali received his bachelor's degree in Electronics and Communication from Brunel University London and a master's in Telecommunications with Business at University College London. He started his career at Spirent as a hardware engineer, and since then has held multiple positions, including solutions engineer and product manager. As I said, he's currently the business development manager for the Americas, focusing on defining complex solutions and helping customers solve their test needs with Spirent's current and future portfolio of services and products. He's an all-around technology enthusiast with a particular interest in PNT, connected and autonomous vehicles, and artificial intelligence. Ali, let's learn more about simulation on the road to autonomy.
Thank you, Alan, and hello, everyone. I would like to start by highlighting open pit mining as a use case. As we just heard from Lee, there has been increased demand for full or near to full autonomy in open pit mining environment. This demand is highly driven by the expected increase in operational efficiency and also safety. Mining has always been a dangerous industry, but autonomy is for sure changing this. More vehicles are being converted from manned to self-driving, and many operations like digging, excavating, and transporting materials are now carried autonomously without much human involvement. Many technologies are used to enable autonomy in mining. For example, GNSS plus Inertial for absolute precise positioning, LiDAR and camera systems for relative positioning and localization, and other technologies as Lee and Raphael highlighted earlier. Over the next couple of slides, I will discuss in more details the challenges related to GNSS to achieve high level of autonomy in mining, and also discuss an example test solution. Okay, so using GNSS in open pit mining has its own challenges that could significantly affect the precision and operation of the overall system. For mining, the demand is not just for positioning at a meter or so accuracy, but rather for precise positioning at centimeter level accuracy. The use of multi-frequency, multi-constellation GNSS receiver with correction data services solve for most of the typical GNSS errors and could enable centimeter level accuracy for most of the time. But there remain some other challenges that affect the accuracy and continuity of the service. Like we heard, multi-pattern obscuration remain a challenge in such environment. Obscuration of the GNSS signal occur as the vehicle dive deep in the pit, causing less satellite to be visible to the system. Multipath could be generated from many sources. For example, the vehicle body carrying the receiver, moving or even static vehicles surrounding the receiver, and of course from other structures within the mine site. All those affect the accuracy of the system to a degree. And then there is space weather. Space weather is another challenge, and specifically scintillation effects. Many mine sites are either on high latitude or equatorial region. And this is a major issue because scintillation effect is mostly active in those two regions. I will discuss more on this later in this presentation. Finally, interference is another challenge in a mine site. There are many different combinations of wireless technologies that could generate interference. Mostly, or I would say the majority of it will be obviously an intentional interference, but obviously those could affect the performance and the availability of the positioning system. Like we heard earlier, correction data service is critical to achieve the accuracy needed for mining operation. There are different correction data services available to use. RTK is by far the most used and trusted service today, but there is increased interest in other services within the mining market. For example, PPP, or even a hybrid variation of both PPP and RTK. This new hybrid approach will overcome the long conversion time of PPP alone. There is still needed for infrastructure with this new approach, but significantly less relative to RTK approach. So like I said, it's expected that autonomy in mining will result higher operation efficiency and safety and less downtime. But also, as highlighted, open pit mine can obscure GNSS signal, hindering continuous operation. So it is important to understand when this will happen and plan ahead to ensure maximum efficiency and safety is achieved. Using geospecific heat maps, 3D terrain models, environmental analysis, and satellite data, Spirent can accurately predict daily GNSS performance and guide efficient mission planning. What you see here is downtown Toulouse, France. The colors represent the number of line of sights available. Red mean more line of sight, as the case in the open square, where blue mean less line of sight, as on in the side roads. This example could be easily converted to an open pit mine site to predict the performance of the system and plan accordingly. Basically, GNSS forecasting takes the surprise out of the positioning performance. So the need for high positioning accuracy in mining, among even other applications, led to increased focus on understanding and characterizing the different errors as a result of space weather and atmosphere. The GNSS signal travels 12,000 miles to Earth. Refraction and diffraction of the signal as it crosses the different layers of the atmosphere can result delays and distortion of the signal. To ensure maximum availability and performance, such errors need to be mitigated for, or at least detected to warn the system of a possible performance compromise. Now let's discuss more about ionospheric scintillation. This is caused by localized fluctuation in the electron density of the ionosphere. This distorts the phase and amplitude of the signal. Typical receivers model are unable to solve for these errors due to the irregularities it causes to the ionosphere. The graph on the screen showed where scintillation events are most frequent. This is mostly around the magnetic equator region and to less extent at the poles. Many mines are located in those regions, hence this issue is important for mining. But keep in mind that scintillation events could also occur in mid-latitude regions of Western Europe and the United States. There are many factors that leads to variation in scintillation properties. For example, time of the day, geomagnetic location, season, and solar activity. In fact, the next solar max is expected to start in 2023, which is even more reasons to test and ensure your system will cope well under a strong scintillation condition. Okay, so given the many errors and challenges highlighted in the previous couple of slides, it's important to obviously test your system to establish the base performance post-integration, as well as tune the system for better performance. Testing could be done using different approaches, like Rafael highlighted, live sky, for example, but such approach is limited and provide no control or repeatability. It's for this reason, simulation approach is ideal for such tests. Using a GNSS simulators give you the ability to control all the different parameters for the 3 different segments of any GNSS constellation. Any errors could be generated and injected in the scenario to enable a good test coverage for typical or even rare errors like scintillation effects. A simulator could be used in conducted mode by connecting the device under test input directly to the simulator RF output, or even in over-the-air mode by radiating the RF signal over an antenna in a controlled environment to test the complete system, including the antenna. We talked about correlation data services a lot today, so obviously that's another important parameter, important output that your simulator should be providing. And for most precise positioning application, it's a big need. So using GNSS simulator, RTCM correction data can be generated and driven to the device under test using different combination of ways, serial or Ethernet port, or even N-Trib. And another element of the system that we talked a lot about today is the inertial measurement unit. And ideally, for a full test coverage, you would like to have a test solution that covers that as well as GNSS and correction data. So it's an essential part of the system to test the sensor fusion algorithm and the different boundaries and errors that can occur within your algorithm. Using Spirent SIM sensor, up to 4 IMU data can be simulated coherent to the GNSS signal with very low latency. The IMU data will bypass the physical IMU and can drive the sensor fusion algorithm directly over SPI or I2C or even over CAN bus using a Vector Canoe software. Finally, I would like to highlight that Spirent, with its more than 30 years experience in the PNT industry, has a complete set of solutions and services that can help you accelerate your development and qualification cycle. Thank you all for listening. Alan, over to you.
Thank you, Ali. We're going to go into new territory now, new territory for today, that is, talking about inertial technology. We'll hear from Alexis Guinamard, who is the Chief Technology Officer and co-founder of SPG Systems in France. SPG Systems is a supplier of miniature, high-performance inertial navigation systems. He holds a master's degree in embedded systems from École Centrale d'Électronique. And since the past decade at SPG Systems, he leads development of cutting-edge navigation algorithms, including AHR, Attitude Heading Reference Systems, Inertial, GNSS, and more. Alexis, please proceed.
Yeah, thank you. Thank you, Alan. So I will briefly present SPG Systems, and then we will dive into the machine control application, which is the topic of today, we will have we will show you a new paradigm for orientation and position tracking, and we will end this presentation by talking also about even more challenging conditions and see what we can deliver for you. Very briefly, SBG Systems is a French manufacturer of high-performance inertial systems that can be used for stabilization and navigation applications. Our headquarters are close to Paris, and we have subsidiaries in the USA, but also in Singapore. We have more than 700 customers and more than 25,000 inertial sensors on the field that are up and running. Since the very beginning, our DNA was to focus on unmanned systems, so really aligned with the topic of today. UAVs, land robots were our main focus, but since then we also covered many other applications like survey and mapping industry, offshore, marine science, camera pointing, antenna tracking, and many other applications. Regarding the products that we deliver, we have a large range of products from basic IMU, just delivering calibrated accelerometer or gyro data, up to all-in-one sensors, fully integrated GNSS, INS systems, but also solutions for survey applications. And finally, we have a post-processing software that is very efficient. We will talk about that later. Now let's talk about the machine control. Traditionally, if we look at the integration of different sensors in a typical machine control application, we have basic sensors like orientation tracker that is used to track the orientation of the vehicle. On the other side, for the position tracking, you use a GNSS receiver. Since you want to have a robust position and also you want to have a heading, sometimes you need to have a good GNSS receiver. So that's why mainly survey-grade GNSS receivers are used. They provide multi-frequency, they provide RTK also for centimetric precision, and also they can provide dual antenna for heading. In this kind of setup, you have simple subsystems. It works well in many situations, but still you have different sensors to install, and you have a very expensive GNSS technology. And finally, since you don't integrate the GNSS and the IMU together, you don't have the best resilience during the GNSS outages. Now let's talk about the very important technologies that need to be embedded into the machine control applications. The GNSS part is a key, of course. Up to now, you had, let's say, two classes of GNSS receivers on the market. At first, you had the entry-level GNSS receivers that were only single frequency. They were low cost, tracking only L1 band. Some of them were trying to do some RTK or dual antenna heading, but they suffered from a very long convergence time, and so their robustness were not good enough to meet the machine control applications. On the other side, you have survey-grade GNSS receivers that are much more expensive because of their multi-frequency design, multi-constellations, but they deliver robust GNSS heading, robust RTK, and they have a better immunity in case of multipath and jamming. The good news is that now you've got the same technology, multi-frequency, RTK, robust position, and so on, but with a much smaller packaging and also a much more cost-effective. So this is what we are trying to leverage on. You will see that. Also, another very important aspect is to maintain a very good performance level, whatever the environment is. So on that slide, you can see two applications that we serve, one snow groomer and one rock breaker. So you can see definitely that on those two applications, you don't have the same temperature level, but still on both of them, if you are operating at the direct sunlight or in a shadow, you will have quite high temperature gradients. Also, both of these applications will have high vibration levels and shocks as well. So this is very important to maintain a good performance level, whatever the environment is. So that's why we developed a very unique technology at SBG Systems and very unique expertise to deliver a consistent and optimal performance. First, over the full temperature range, we developed an improved calibration procedure using high-end calibration devices, 2-axis rotary tables with temperature chambers. All our sensors are calibrated using these specific tools. So that's a very key aspect of our technology. But also it's important to make sure that we deliver a good performance for every unit that we deliver. So that's why during the production process, we have a screening process. We make sure that if one sensor fails at one parameter, one specification parameter, we'll just not deliver it. It's too important to make sure that all the sensors behave exactly the same. And also over the full lifetime of the product. We select only industrial grade sensors with a specific packaging in ceramic, or we also have in-house qualification process to make sure that we will maintain the best performance over the full lifetime with no drift over time. On the sensor fusion side, some of you might be aware of the Kalman filter that is the core of inertial navigation systems. On one side, you've got an INS, which will provide precise position and attitude during short-term GNSS outages. And on the other side, you've got a GNSS receiver that will be used to stabilize the position, velocity, and orientation. This stabilization process is performed by the Kalman filter itself. However, please remind that EKF is not magic. This is the theory. But in the real world, the accuracy will still be driven by the IMU that you are using and the GNSS. So you need robust sensors at the inputs of the Kalman filter. And also from time to time, you should expect faulty measurements, especially from the GNSS receiver. If you have multipath, you can still have, even with a good receiver, you can still have faulty measurements. So it's important to detect that and exclude these measurements from fooling the Kalman filter. So this is a specific technology that we developed at SBG Systems to make sure that we have robust navigation outputs. And here comes our new product. Here I present the Ellipse D, the new Ellipse D, which can be very suitable for machine control applications. It can be integrated in many applications, of course, but for machine control, it's very excellent product. It integrates all the components that you need in a single package. A robust GNSS receiver with multi-frequency, RTK, dual antenna, robust IMU with best-in-class calibration, as I mentioned, and also a cutting-edge INS GNSS sensor fusion algorithm. So in order to get a very good position, you need only one sensor and two antennas to get your accurate position. This Ellipse D represents a turnkey solution and is delivered at a fraction of the cost compared to traditional integration that could be done up to now. So the key advantage of this product is also the small size. It is only a few centimeters wide, and also the integration between the GNSS and the IMU allows to improve the resilience in case of GNSS outage. If we have a look at the advantages, so as I mentioned, the GNSS, very important aspects. Here we have quad constellations, dual frequency, RTK capability, but it allows to deliver reliable navigation even in difficult GNSS conditions. We also have dedicated motion profiles that minimize the position drift during the outages. For instance, we have a truck or automotive motion profile for on-road applications. Also, we have specific tools like CAN bus outputs or automatic lever arm estimation. We can fuse the inertial data with odometers like CAN bus odometers or pulse odometers. So this product is very interesting, also compatible with ROS operating system with a specific driver and RT maps for those who are integrating these softwares. But the Ellipse D is not alone. That's a complete line of product that can be also used in many other applications. We have on this full product line, we have a performance of 0.05 degree on the roll and pitch and 0.2 degree on the heading, with also 1 centimeter precision on the position side. Another very nice tool that I would like to highlight, even for machine control application, is Inertial post-processing software. So traditionally, we use post-processing to get the ultimate performance in a forward, backward, and merge processing that is used typically in survey applications when you want to get the best performance. However, even for real-time application, it can be very nice to use Inertial as an analyze tool. You can replay your sensor data with different configuration to make sure that you have a proper setup, and also you can refine your lever arms using a specific calibration procedure. So even using this calibration procedure, you will be able to enter back the refined lever arm into your system firmware. And in that case, the real-time performance can be really improved. So that's a very interesting software, also to be coupled with machine control applications, especially during the R&D phase. Now we will see that even if you have more challenging conditions, we have also other solutions. If you have a need to get reference data, sometimes it is necessary if you have an autonomy project, or if you operate in an urban canyon environment. Whatever your autonomous platform is, we might have a good solution for you. For the highest, for these applications, we have higher performance products with dedicated algorithms. As I mentioned, specific motion profiles for automotive applications, tight coupling capable sensors. All of these products can run in real time or in post-processing. So for the highest performance products, we have the NavSight series that can be delivered with multiple performance grades. We can range up to 0.004 degree on the roll and pitch, 0.008 degree on the heading. And this product will work very nicely with Inertial post-processing software. But we also have more compact products. If you have already a platform that you want a sensor to be integrated in it, with the Equinox, for instance, or even with Quanta product line, which is maybe the best suitable if you want to deeply integrate your sensor. So here it is an OEM based product, also provided with 2 levels of performance, very low power consumption, and capable also of doing real-time post-processing. So yeah, that can be a very good product also for autonomous platforms. And this will conclude my presentation. Thank you for listening, and Alan, you you can have the mouse and the talk.
Thank you, Alexis. I accept the mouse. I accept the talk. And we are going to have some questions in a few minutes. But first, we give the audience a look at some further resources for you. No need to jot down these long links. You will get the presentation in your email, so you'll have them handy. But this is just a quick preview of what's coming up in your email. And then one more question for you to answer to let us know what type of testing you're least familiar with.
Absolutely. And in this case, you have 3 choices there. And again, just to reiterate, we are looking for the testing that you are at least familiar with. Live sky GNSS testing, simulation of GNSS plus INS, record and playback. All right, looks like 19% saying live sky GNSS testing, 53% simulation of GNSS plus INS, and 28% record and playback.
We're going to turn back to Ali with the answer to that question. And that's a cue, if I ever heard one, for him to talk more about simulation of GNSS plus INS. And in that context, Ali, we do have a question for you. How much do you trust your positioning system once it's deployed, and how often do you verify, given that the GNSS constellation is in flux?
Yeah, thank you, Alan. That's a good question. You should trust your positioning system, of course, but only after good test and verification has been carried. As we heard, edge cases must be tested to ensure the system cope well with those cases, especially those edge cases related to the actual application and the environment where the vehicle is running. If we look at the mining site as an example, where the environment is always changing, using forecasting service like what I highlighted earlier, that should give the operator a good prediction of performance and more trust in the system, of course. Finally, I would like to highlight also other tools like Sim3D, which is a way to replicate the real-life scenario in 3D modeling and ensure that the testing is as realistic as possible, which then helps add more credibility to the level of testing as a result of the increased, trust, and obviously result in increased trust in the positioning system. So I hope that answered the question.
Yes, good answer. Alexis, we've got a question for you. What's the startup time required to get valid data?
Oh, that's a good question. So typically, all inertial systems need some time to initialize, to stabilize. We say that typically we need about 10 minutes to obtain the optimal performance. However, keep in mind that you can still use the product very, very quickly at the first samples that we deliver, since we deliver also standard deviation outputs. It is the sensor is already usable, and since we are using a multi-frequency heading solution, we can obtain a fully initialized system within just a few seconds. So I would say that within a few seconds you can get your data already usable, and the best performance can be obtained after a few minutes of convergence. But in a typical condition, there is no need to wait for that.
And Alexis, can you comment on CAN odometers? Do you have a list of compatible devices?
Sure. So I don't have a list of compatible devices because we have developed our interface to be as flexible as possible. So virtually it is compatible with any CAN bus odometer on the market, even if we don't have their specification. So when the customer needs to use this CAN bus odometer, he can configure very precisely how the message needs to be interpreted, how we need to read the velocity from the CAN bus. And in that way, we will be compatible with all the velocity information coming out of a CAN bus in every vehicle.
Thank you. I've got one question here I'm going to field myself. Is it possible, someone wants to know, is it possible to obtain less than 1 meter accuracy with low-cost GNSS receivers? And the application this listener is talking about is in ports and harbors. And first of all, I'm going to refer that listener to tomorrow's webinar, where we will be talking about getting good accuracy results with low-cost GNSS receivers. Generally, this the 1 meter accuracy is not something one can achieve, but with special algorithms that we'll hear about tomorrow, special algorithms and low-cost components, both GNSS and Inertial, you're going to approach that. Ports typically need better than 10 centimeters accuracy, especially for reach stackers and forklifts, and you'll also need it for machine navigation around the yard. So that's a partial answer to your question. Tune in tomorrow for more detail. Lee, I know you've had lots of experience in on-road autonomy, where the safety levels are fairly well defined and understood. How is safety in the mining environment? What requirements, levels, standards are there?
Well, there's since autonomous hauling has kind of been around for a while and is actually quite mature. The way it started is the safety regulations and regulating autonomous machines, hauling machines, just hadn't caught up. And so really what the OEMs and the folks working on autonomous hauling, you focus on making the human safety standards and applying to those. And you still have the machine, and we'll have all the ISO standards for the braking systems, steering systems, and all those types of systems. But that really hadn't caught up with hauling. So you really had to demonstrate that it's safer than a manned operation. And the way you did that is you did it through a lot of simulation and lots of FMEAs and lots of things like that. But you also did it by controlling the environment. You would just take variables out, like, for example, humans. You just say, okay, we'll detect humans, but your first order of business is keep all the humans out of the autonomous area. You keep keeping humans out, and then you control. Another one is vehicle-to-vehicle interaction, especially large haul trucks and light vehicles, pickup trucks. So then what you do is you make sure everything inside an autonomous area is instrumented, you know where it is. That's where that command and control comes in. So you basically were focused on making it safer than a manned operation. And that's, I think, what the folks that are focused on it have done that and have determined that they can make it safer.
Safer than a manned solution. That's it's really incredible to me that, but credible, believable that is possible. Ali, a question for you. For the example test solution that you presented, can the user also simulate interference and spoofing effects?
Yes, the short answer is yes. Spirent test solution presented is also capable of simulating both interference and spoofing in the same scenario without the need for any additional hardware. Both in-band and out-of-band interference could be simulated. I mean, for example, in the simulation scenario, the user can define multiple interference sources and place them along the trajectory. The simulator will then output at the same RF both the low-level GNSS signal and the interference signal. The interference signal also is modulated based on how far the device under test is away from the interference sources. And the same with spoofing. There are multiple ways to do spoofing in a Spirent simulator. We also have multiple dedicated software solutions that allow to do more advanced interference and source and spoofing for multiple applications. Okay.
Thank you, Ali. Lee, we've been talking about mining, open pit mining operations. What about machine positioning in underground mining?
Yeah, that's an interesting one. Block cave mining is an interesting deal. So if anybody wants to look up a block cave mining, and that's basically a controlled collapse of a mine, and you basically take the ore out of chutes. So you have these load haul dump machines that run around underground, but you have to know where they are in those tunnels, and it's inherently dangerous in those environments because you have a controlled collapse. So what you do is you can't use GNSS receivers, obviously, because you can't go through solid rock. So typically what they'll do is utilize some sort of a SLAM technology and LiDARs or something like that. And so what you still have to know exactly where you are in that tunnel, and you have a accurate map of the tunnel that you're going in, and then you basically use your 3D point clouds to overlay it so you know exactly where you are inside that tunnel. So that's typically how at least I'm familiar with it. There are probably many ways of doing it, but that's one way.
Interesting. Alexis, a question for you. What's the duration of the full lifetime of the SPG navigators, and how much do the errors grow between shipment and the end of the device's full lifetime?
Well, that's a good question, Alan. In fact, we have records that show that we have almost no drift over the full lifetime. We have products that have been running for more than 10 years, and when we get back them for any support, we see that the errors are very, very close to what we had during the calibration. We still have some customers that want to have, some stamps saying a guarantee, and they want to have regular recalibration. So we have also the possibility to check the calibration regularly on a regular basis. So we can do, for instance, it every 3 years, but we can see that in practice there is no need to do so, and we see that 10 years is a typical lifetime for MEMS sensors.
10 years can be a very long time, and it's quite remarkable that there's no degradation in the sensors functioning over that lifetime. Lee, back to you. I know that with AutonomouStuff has been known up till now primarily for on-road, and now building an increasing reputation in off-road autonomy. What is the difference in localization methods between the two environments, on-road and off-road?
So from an on-road standpoint, it's probably best to give an example of like what AutoWare and how AutoWare does it. There'll be some similarities to anybody developing an on-road autonomy stack, and that's the high-definition map. So localization, obviously you want to know exactly where you are on the planet at all times with an absolute position, but knowing your position relative to other objects such as curbs, traffic lights, and all that, that's typically where you need to localize on a high-definition map. And then you will know what's coming up. For example, you'll know if there's a traffic light. So you use basically a high definition map that's fully annotated of the driving area, and obviously that's quite expensive. In an off-road environment, you don't need to be quite as dependent and need a high definition map where everything's annotated and all that, because you can control the objects, like people, other machines inside that area. So you don't have to go through that all the time to make a high definition map. You can use a lower fidelity map and control the interaction of the vehicles and do it that way. So that's the big deal is the high definition map.
Mapping makes the difference. Well, we've spent a very profitable hour and a half delving into machine control aspects of autonomy, or autonomous aspects of machine control, however you would like to look at it. We're going to continue tomorrow. I want to remind our audience that come back here, same time, same place, same channel. Don't adjust your set. Don't touch the dial, because we will be talking about autonomous ground vehicles in the precision ag realm primarily. There will be ramifications for other environments and applications. The sensors we'll be discussing will be GNSS, of course, and inertial. We'll also be talking about GNSS corrections and perception sensors in the off-road environment. We will have a debut, so to speak, of a dramatic, dynamic, and very surprising capabilities in a new product for the off-road environment. So you'll want to see that. You'll be among the first to see it in action. I can't say more. I'm not allowed to say more. But tomorrow we'll see. Will data fusion, situational awareness through precision perception, and software stacks all come into play there. The Autonomous Week is building to its climax. We've had drama and high technical advances throughout. They will continue tomorrow. You will receive next week. Lori will give you details about this in a moment. The contents of this webinar to peruse again, and I want to thank our panel: Lee Baldwin from Hexagon AutonomouStuff, Rafael Gretsch from Spirent Communications, and Ali Suleiman, also from Spirent, and Alexis Guinama from SPG Systems. I want to thank our sponsors for today, the three companies who furnish the speakers. I want to thank everyone around the world for attending and listening. It's always profitable for me to conduct these webinars. I learn a great deal. I'm sure that you all have as well. This is Alan Cameron from Inside GNSS and Inside Unmanned Systems, and I can now say we have a new publication and website you'll be hearing about very shortly: Inside Autonomous Vehicles. Thank you once again for attending. And Lori, before we turn to you, I'd just like to give all of our panelists a chance to make any concluding comment or farewell to the audience. Lee, let's start with you.
Yep. Thank you very much. I appreciate the offer to speak today. Hopefully it was valuable.
Rafael, a closing word?
Yeah, same here. So yeah, thank you so much for giving us the opportunity to speak. And yeah, join us again tomorrow for more interesting information.
We will be back. Ali?
Yeah, thank you all for attending. I hope you found the material useful, and feel free to get in touch with any thoughts or questions that you may have. Yeah, see you tomorrow.
And Alexis?
Yeah, thank you very much for this very interesting talk. It's if you have any question, feel free to contact me.
Wonderful. This is Alan Cameron signing off. Lori, over to you.
Well, thank you, Alan. And most importantly, thank you all for joining us. And this is Lori Dearman saying, hope we see you tomorrow.